So, hello everyone. Welcome to our third NICARA seminar. Today I have my colleague with me, Dr. Yong Lee, our clinical neuroimaging expert. Together with him, I will guide you through the seminar. My name is Markus Butz-Ostendorf. I'm from Biomax Product Management. I have a background in neuroanatomy and neuroinformatics. And at Biomax, I'm responsible for all the brain science projects and products. So today we will have, first of all, a brief introduction to Biomax, but then we have a scientific talk. Afterwards, a live demo of NICARA by my colleague Yong, and thereafter we have a question round. Before we actually start, few organizational things I would like to mention. So please make sure that your microphone is muted and ask your question in the discussion round after the live demo. We are very happy for an interactive discussion, and we will record the video, the live seminar, and upload this later on to our YouTube channel. Please note we will exclude the discussion round, so don't be worried. We won't have you on tape, so you can ask your questions without being recorded. Afterwards, all registrants will receive a summary and also the link to the YouTube video. So, Biomax is a German company. We are for more than 20 years in the market. And we are specialized on knowledge management solutions for the life science industry. Especially, we offer clinical information systems. We offer solutions for synthetic biology, and the latest products and projects are in the field of brain science. Our technology is validated through multi-year contracts with reference customers and thousands of users worldwide. We currently have 45 employees, and we are at Biomax, we are life science experts as well as software engineers. Biomax is fully GDPR conform. We are certified ISO 9001 and ISO 27001. So let's start with the scientific talk. During this talk, I will focus on using connectomics for aging studies, and especially on putative new biomarkers derived from neuroimaging, particularly from connectomics for aging and dementia. So let's first share some ideas on biomarkers and what people say from clinics and also from pharmaceutical industries, what biomarkers should look like. So ideally, they shall be easy to obtain. They shall detect and quantify brain changes, especially those that precede gross atrophy in aging and neurodegeneration. Biomarkers should, of course, respond to treatment and may serve as an outcome biomarker in clinical trials. Of course, biomarkers shall be reproducible and reliable. So far, we use, or volumetric measurements are widely used for aging studies as biomarkers, but they suffer from a moderate prediction quality. Very often, in addition to imaging biomarkers, cognitive testing is needed, but cognitive testing is time-consuming and expensive. Therefore, the research field is looking for more sophisticated biomarkers that, for example, also combine different imaging technologies, for example, PET MRI, functional magnetic resonance imaging, or DTI, diffusion tensor imaging. And those can greatly enhance prediction quality. That's what we are going to focus on in this talk, and especially those biomarkers that rely on the connectome. Connectomes can be extracted from structural and functional imaging, so particularly from DTI tractography. You can see which brain areas are structurally interconnected. This gives you the structural map of connections, the structural connectome, or from time series correlations. So from time series correlations measured by functional MRI, MEG, or EEG, you can also construct a functional connectome, a functional map of all the connections, the functional connections in the brain. It is well described that the connectome is directly affected by neurodegeneration. So some authors have even described the Alzheimer's disease as a disconnection syndrome of neural connections. We also know that connectome alterations correlate with cognitive impairments. And, important for this seminar, antidementive treatment was reported to have a protective effect on the structural and functional connectome. So it makes sense to look more into depth of the connectome and how to extract connectomes from imaging raw data. And here's exactly the problem why it's not often used in clinical applications and aging studies, because extracting connectome from raw data is time and cost intensive. You need expert knowledge in neuroimaging, and you need large hardware resources to process connectomes and run processing pipelines. So the main question here, and that's what we are addressing in this talk, in this webinar, how can we improve neuroimaging-derived biomarkers from DTI tractography for a more precise patient stratification and for a better monitoring of treatment outcome in aging and neurodegeneration studies. This is the solution we are offering by Biomax. So NICARA stands for Neuroimaging-Based Connectome Assessment in Research and Application. This is a client-server-based tool to automatically extract connectomes from raw imaging data. It provides a fully integrated study management. You have catalog functions for connectome data, and you have ample functionalities for visualization, for exploration data, and also for comparing connectomes between patients and matched controls. And how this all works, I will show you during this talk, and will also show you the applications. So here is a screenshot from our Connectome Builder, the tool in NICARA by which you can upload neuroimaging data, raw imaging data to our secure servers and run the pipelines fully securely and fully automated on Biomax hardware. There is no expert knowledge required, and at the end you get nice visualizations. So for example, here in this image space you see a native brain, conventional MRI T1 weighted, and overlaid you see a fiber density map indicating which area has a high fiber density for a particular white matter tract. So for example, here is the cingulum white matter tract, and every voxel basically is color coded depending for whether it has high connection fiber density here for this cingulum tract here in red, or lower fiber density here for indicated in blue. And we have several major white matter tracts which come out of the box and allow you to add a further dimension to this conventional MRI image. Our algorithms in NICARA also allow you to quantify this image, and what you see here is now basically what we call the feature space. So we basically abstract away from the detailed image and just represent the features. So here in that sense brain connectivity. So the points are the regions of interest, basically the center of mass coordinates here of each region of interest. And every connection here, every line indicates a connection between these points. So the stronger the line and the darker the line, the stronger is the connection. So that means we not only show the white matter tract, but we also know the connections that belong to this white matter tract. So all the brain areas of this white matter tract that are interconnected. So a higher level of detail here, finer grained detail, and especially quantified so that we can really make comparisons. Here's an example. So that's the Connectome Comparator. So in the Connectome Comparator, you can make, for example, assessments over time. You can see here, and my colleague Yong Lee will show more examples in the live demo. You can see how the connections change over time. So this is here depicted by the graph, and also here by bar graphics and also a tabular listing. We come to that in more detail during the talk and during the live demo. So the main functionality of NICARA to extract connectomes from raw imaging data is realized by processing pipelines. The important bit here is that those tools that we use are all open source. So we basically have selected the best and most documented tools for image pre-processing and processing, and have assembled them to a pipeline. You see the segmentation here. For example, all images are immediately skull stripped for data protection. And then we do the pre-processing of the diffusion data sets, and finally do a deterministic and probabilistic tractography. And that leads to the fiber tracking and the connections that you saw. All tools are validated in hundreds of published studies, and very recently the tools that we have chosen and the pipeline we have assembled was described and suggested as preferred neuroimaging method, especially for Alzheimer's patients and neurodegeneration. Here now you see the cingulum connections again. So basically we have done a full brain tractography, so we have all possible connections measured, and now we apply a filtering so that we only see those connections that belong to the cingulum in the Alzheimer's patient and also in matched controls. And what you immediately see is that the matched control has much stronger connections and also more connections if you compared to the Alzheimer's patients. This is just one fiber tract, but we see similar pictures in other fiber tracts. And this, of course, cries for a group comparison to validate these findings. Here's the group comparison. This has also been done in NICARA. These are just a few mouse clicks, and then you get the average and the standard deviation of the patient here in dark bars, and green are those for the control. At the x-axis, we see all the different connections that we have now included for this comparison. And what we basically see is that we don't see very much. So even though this is a small sample, so we have about 10 patients against 20 matched controls, if we would increase this, we could perhaps reduce the standard deviation a bit. But if you look at the trend here, there is not a real difference between patient average connection strength and healthy controls. And that's also the case for another fiber tract, the superior longitudinal fasciculus. The superior longitudinal fasciculus is worth to pay attention to because it involves the hippocampus, and the hippocampal formation is known to be affected in Alzheimer's patients by neurodegeneration. Here is a slight trend visible, but also not really clearly. So we asked ourselves, how can we improve these results, and is the group comparison really the right way to go? And what we thought is, perhaps it's so that every patient is different, and it's necessary to compare the individual patient against matched controls, and that's what we are doing on the next slide. So here we have the cingulum fiber tract in the top row again, and the SLF, the superior longitudinal fasciculus, at the bottom row. So here in our box plots, the colored boxes indicate the controls. So every connection here is again labeled and shows the average and the standard deviation for the age and gender matched controls, for example. We see some outliers, and importantly, the patient here is labeled by a black mark here, the diamond with the bar. So you see basically that the patient follows very much the profile of the healthy controls, but in total it's all attenuated, so the connection strengths are attenuated. And if we look at the superior longitudinal fasciculus, we see a similar picture. In some connections, the patient is still doing good, like in this one. In others, he has more than twice a standard deviation less than the controls. And now we compare also these results to a second patient and see if we see the same trend. And here we see, yes, the pattern is basically the same. So the patient follows basically the pattern of the healthy controls, again attenuated the connection strength. But what we also see, and it's clear here for both tracts, that every patient has different connections which are degenerated. So that means if you compare the group averages, then it becomes obvious that the differences cancel each other out. So some patients have strong reduction in some connections, but not all patients, and then the average is again closer to the normal average, and at the end you don't experience the clear group differences. The next question we had is, how does a mild cognitive impairment look like in comparison to healthy controls, but also in comparison to the Alzheimer's patients? And that's what I'm showing you on the next slide. So here we have the same fiber tracts, cingulum and SLF. And here we see some connections which are a little bit reduced. But overall, we see a different pattern. We see that MCI patients even show some connections with increased connection strength, especially here in the SLF. So we speculate that it could be a compensatory mechanism going on in MCI patients, that some connections really become stronger as a consequence of other connections degenerating. So it could be that this is part of an ongoing process that further needs to be explored. But the essential thing here is, to better understand this, we need to look at the dynamics of the process. So ideally, we have a longitudinal assessment and K and MAC comparisons between 2 time points. And that's what I'm showing you now. So here first, I would like to show you the dynamics, the rewiring in a healthy control. So basically what you see here on the x-axis are the percentage differences compared to a T0, the first time point measurement. And so left from 0 are degenerating connections, right are increasing connections. And the connections are here at the y-axis. So every line here that you see here is basically one connection in the cingulum fiber tracts, so these are very many, and we have sorted them according to their strength so that you can get this clear picture. We couldn't label all the connections because there are just too many, but that's the idea. And what you see here is that in a healthy human, we have ongoing degeneration of synapses, or basically fiber tracts, so to say. And at the same time, we have a formation of connections, or basically an increase of other connections. So that's what we call rewiring, and this is a spontaneous and fully physiological process. So when we compare now the MCI patient with the healthy control, then we see a little shift here. We see that the proportion of degenerating connections has increased compared to the formation, or basically the increase of connections. So that's very remarkable, and I come to that in a second again. And the Alzheimer's patient has basically a reduced degeneration and a reduced increase of connections. So we could say it has the Alzheimer's patient has a decreased plasticity, a decreased rewiring. So also if you look at the SLF, we see very much the same picture. Not only look at the intersection here, but also look at the shape of this pattern here, this curve here. You see somewhat convex curve that further underlines the reduced changes in fiber connectivity. You can also label this. So if we draw these triangles, this becomes very clear. And if we are interested in testing drugs and or drug candidates, for example, let's assume you want to test a drug candidate that has the potential role in slowing down degeneration, and you want to test the outcome, then it makes sense not to include the Alzheimer's patient because they have a reduced synapse degeneration or connectivity degeneration already. So it would make much more sense to look at the mild cognitive impairment patient, because if you compare them, they have an increased degeneration compared to matched healthy controls, and especially compared to Alzheimer's diseased patients. So that speaks very much for a good patient stratification, especially when it comes to the selection of patients for clinical trials. No matter whether it's a mild cognitive impairment patient or an Alzheimer's disease patient, every patient is individual, and you need to look at the current status, the current dynamic processes of brain rewiring in the individual patient, and therefore it would be optimal to have longitudinal assessments of these of the subjects you want to include. Here we had a time interval of 1 year between the assessments, and that gives a good indication. So I think that's a very interesting result so far, and this offers many potentials for biomarker candidates, and it's very clear and very easy to interpret, and that needs to be assessed now and further validated in clinical studies. We have done this with ADNI patients, and the results are very promising. We are going to publish this now, but whoever has data and wants to test this with his own or her own data, please get in touch with us. So let's summarize the results from this proof of concept study here. We can say that every connectome is different, and group comparisons are less meaningful. We really need to aim for personalized medicine here in the field of neurology to really assess the individual pattern of or personalized pattern of fiber
has joined the meeting.
has of fiber degeneration. Interestingly, mild cognitive impairment patients show the most increased fiber degeneration, but at the same time, potentially a compensatory increase of individual connections. So, taking this together, longitudinal assessments are really needed to reveal the properties of brain rewiring in the individual subject and can help differentiate between Alzheimer's patients, MCI, and healthy controls. If you are interested in the underlying principles of brain rewiring, I would like to draw your attention to a book that I published 3 years ago. This is beyond the scope of this webinar, but you find the biological principles of brain rewiring, and in a sense, this is a nice continuation to have now these mechanisms be found in imaging studies. The value proposition for clinical studies of NICARA is clearly a more precise patient characterization by an earlier detection and of accelerated neurodegeneration. We can better monitor the outcome of treatment by full brain tractography before and after drug treatment. No expert knowledge is needed and no hardware resources are needed there, provided by the cloud solution. With this, I'm at the end of this proof of concept presentation and scientific talk. I would like to hand over to my colleague Yong Lee, our clinical neuroimaging scientist, who will now show you how you can use NICARA to do the assessments, similar assessments that you have seen, and will give you insights from his daily work as a clinical neuroimaging specialist. So we will meet back in the live discussion round.
Good afternoon, everyone. My name is Yong Lee. I'm a neuroimaging scientist in project manager team at Biomax. In this live demo, I would like to show you how to use our latest product, NICARA, neuroimaging-based connectome assessment in research and application, to create connectomes from raw image data, as well as explore the connectome result with components included in NICARA. So 3 main components will be highlighted in this live demo: Connectome Builder, Connectome Browser, and Connectome Comparator. Suppose I'm a neurologist. I have some new treatment ideas for my Alzheimer's disease patient and as well as mild cognitive impairment patient. I've already collected MR images for those group of patients as well as matched controls. But I only have a little time after my clinical work. Neither do I have sufficient resources to install, explore, and use the state-of-art neuroimaging analysis software, open source softwares. Nor do I get access to high-performance computing servers. Moreover, I'm no expert in neuroimaging analysis technology. After a certain time of struggle, I found NICARA. Let me show you how I explore my research ideas using NICARA. Here is the landing page of NICARA after you log in. On the left side is detailed information of your project, feedback button, as well as contact for support. In the middle column, there's a tile menu, include all the 4 components included in NICARA at this moment. The 4 components are Connectome Browser to explore connectomes, Connectome Builder to create and upload connectomes, Connectome Editor to create and store subnetwork of the connectome, Connectome Comparator to make comparisons between connectomes. I would like to first process my raw imaging data of my patient. So it's clear that Connectome Builder will be used. In the Connectome Builder, normally user have to input new subject and a study. To save time, I simply use already existing subject and project. You simply click on the starting DTI workflow, input information, so here is the identifier for connectome result. In the cohort, I can choose control patient or intervention or placebo. Luckily, I have a longitudinal design, so I'm free to choose either by time or by event, pre-op, post-op, or by sequence, first follow-up, second follow-up, etc. So here I put day 1. Full screen. Okay. So now it's much more clear. In the second tab, I input technical details, technical parameters. Last, I input the raw image data. As required, there's 4 files are required: BYL, BWAX, DTI data, and the T1 data. DTI and the T1 weighted image are in Nifty format. After it's uploaded, simply click on Start DTI Tractography. The job is submitted. So worth to notice that the Nifty file format is not a default output format of image from every scanner, whereas DICOM format is a default. Thanks to the NICARA developing team, I got a little help from them to help me to convert DICOM format to Nifty format, and as extra service. And I really appreciate this in the long run to help me to to easily input my patient's data. So when the job submits successfully, I can directly go back to the Connectome Builder landing page. As you can see, my patient is in progress. After the process finished, I will get 1 email notice, and I also can find my patient's data here. So the first thing I would do after the process finished would be quality control. Simply click on one of the subject. And first I would check the image segmentation quality control report. In this report, in the middle column part, the green scores represents the image and the processing quality. When it's green, it's high quality. I'm happy to see that. On the right side, on the right column, there are morphometry measures, including volumes for different tissues, CSF, gray matter, white matter, and also the total intracranial volume estimation. Also, there are surface reconstructed thickness of gray matter. This is a good indication of aging, for example. The colorful images are, on the left side, original T1 image. On the right side is the intensity normalized T1 image. Both images modalities are used to segment the volumes of different brain tissues. Those are gray matter, white matter, and CSF. Below, the grayscale image shows how well the whole brain separated or stripped from the rest of the tissue. That means vessels, dura, and CSF. And we can see that there's no white matter hyperintensity. The next step, I would like to check image registration. In the image registration report, we see two images modality. On the left side, this is DTI B0 image. On the right side, it's a T1 weighted image of this same patient. As you can see, both modality are well correlated.
Has left the meeting.
And both are well registered, which is very, very important for the later analysis to recreate ROI-based whole brain probabilistic tractography. So now I would like to see some images result of the Connectome. Back to the landing page, I go to Connectome browser. So I go to the Alzheimer's patient study, and it's very convenient that it's allowing me to filter my patient, for example, with age range. And I remember this patient is a typical Alzheimer's patient. I have a look. His Connectome result. In the Connectome result landing page, I simply click on 3D anatomy. So here we go, the 3D anatomy in native space of this patient. So I choose sagittal plane. Very nice. NICARA already by default provide 9 predefined fiber tracks cover the whole brain. So I see superior longitudinal fasciculus, which is typically impaired in Alzheimer's as well as MCI patients. Let's have a look. So the sliding bar provide very convenient scrolling from slides to slides to view my patient, to view my patient's image. So the fiber density map overlay on the native T1 image is simply a heat map representation of predefined fiber tracks, and that means how many fibers get through each voxel, which come from this predefined fiber tracks, extracted from a whole brain probabilistic fiber track with a total streamline 50 milli. I see that the warmer area represent high streamline get passed through. So yeah, this is nice. I can estimate a little bit reduction of SLF, superior longitudinal fasciculus, but what about the control? Here is a control result. So we can see clear differences. This is patient, this is control, this is patient. And yeah, this is clear. This is also logic, but still abundant information in the image space. So what NICARA can offer in the feature space of Connectome result? Now I simply go to Connectome result of this same patient. Connectome result is represented in 3D lattice graph. And as you can see, this is in 3D a representation and of this SLF fiber, and you can see the asymmetry of this patient between two hemispheres for each individual connections. And yeah, I see maybe there are some reductions, but I'm not sure. Let's compare to one matched control. While it's loading, let's have a look. And as compared to the image space, the feature space provides a good overview, not only from one side, also from the other side. The thickness of each line represents the connectome strength between two rows. Okay. It's been loading, and yeah. Well, this is the feature space, and it's more or less logic as compared to the image space. And so my question is that, okay, so this is one-to-one point comparison. I can expect the loaded control subject will have a more abundant connections as compared to this. But this is only one-time point comparison. What about the aging effect of the group of controls as compared to this patient? And because that will help me to make sure that this reduction is directly related to the pathology instead of, which is beyond the normal aging. Therefore, I would like to try the comparison between single patient and matched controls. I go to the landing page. To perform this comparison, I go to Comparator, and I go to the Create Patient Report. Now I select my patient. I select the first measurement time. I apply multiple filters to filter my subject. There's a typo. So I have 12 matched controls available. Next, I still choose the superior longitudinal fasciculus. Now, while it's loading, I realize that this is how convenient it is. NICARA provides the chance for me to form a group comparison or all kind of comparisons of connectome. Previously, I have to extract the connectome result or connectivity result of each patient or controls. And sometimes I have to write a script to do this and to arrange them in the right format and then do the group comparison in SPSS or Statistica, and then to get some plot. Now, only need few clicks, I can get some kind of plot very quickly to explore my research questions. So here we are. the connection comparison summary appeared in the middle part. So here is the comparison information, patient information, subnetwork information, and let's see the patient report. Excuse me, I forget to check the connections. Yeah, it's yeah, sometimes I click too fast, and yeah. Okay, let me show you the preloaded result to save some time. So here is the as my colleague Marcus showed you before, and this is the Alzheimer's patient SCF result, and as we can see, there's a general reduction as compared to matched controls. So Alzheimer's patients DTI structure connectome indeed show in general reduction as compared to controls. What about the MCI patient? So the MCI patients show some reduction for some connections, but not so clear for the rest. And so far, it's only one time point, patient versus matched controls. And there are still a lot of information. And it's very nice plot. I can take a photo to register and for the later analysis, but I need something more. And I need to see the dynamics of patient changes according to time. So nicely, NICARA provide the longitudinal comparisons. So I perform the longitudinal comparisons, and here is the result. Here is the patient's longitudinal comparison. You may be familiar with this plot. The horizontal bar plot represents the percentage differences between first measurement and the second measurement of the patient within all the detailed connections within the superior longitudinal fasciculus. This is patient's data. Here is MCI patient data. And the third is the controls data. And I guess some of the tabs need to be reloaded. I apologize for this technical issue. Yeah. So in this comparison, I see the clear curvature differences between Alzheimer's, MCI patient, and matched controls. It takes a little bit while. Okay, so it's clear already between Alzheimer's patients, mild cognitive controls, and this is not only one, but so here is another Alzheimer's patient as compared to MCI. This is clear. And here is another one. So a little bit different characteristics as compared to MCI. And when it's loaded, the controls showed another pattern. So patient, MCI, and control, they show different characteristic for the longitudinal differences comparison for the superior longitudinal fasciculus. So this is make a lot of sense, since in the daily clinical routine, I also treat the patient individually. So personalized plan for treatment make a lot of sense. Therefore, and this DTI structural connectome information of the dynamics of a patient's disease progression is very, very important and can serve as a connectome biomarker for me to screen my patient to further explore my research ideas. So considering the longitudinal measurement require a little bit more effort, I better collect a long list of patients and calling them right now. So before I close this left session, I'm gonna check whether it take a little bit longer time. Well, as my colleagues already shown that, this is clear that the patient versus MCI versus control, they show different connectome longitudinal comparison pattern. So I better call my patient now, and this is end the this left demo, but it starts the NICARA assist pharmacologist, neurologist, and scientist to provide precise and early diagnostics and optimal personalized treatment so as to improve the living condition of broader range of patients. And I really appreciate your attention and interest and consideration. If you have any questions, please unmute your microphone. Feel free to ask.
Yeah, so thank you very much for this live presentation to you, Yong, and whoever has questions, please type them in the chat or just unmute your microphone to start an online discussion. So I would like to draw your attention to the fact that we also have demo accounts for NICARA. So you can just type in nicara.eu and you reach the login page of NICARA. You can register a demo account yourself to watch the process data, which is there already. And if you like to process your own data, get in touch with us. We can also give you a full account for some time to test NICARA at the full extent and talk with us over about potential studies, what you want to do, and use it for what you want to do it, use it. So I don't see any question in the chat. We are still well in the time, so if you have some questions later on, or once you have set up your free demo account, feel free to just drop us an email if you have any questions. So we can also discuss this in follow-up sessions if you like. No problem at all. Doesn't need to be addressed right now. Take your time. I thank everyone for joining and watching our webinar. And yeah, hope to see you soon and continue the conversation about NICARA. Thank you very much, and bye-bye.
Thank you. Bye.